Hi, in this Shader Stories series, we're looking at visualizing the Mandelbrot set. In the first part, we went as far as producing the Mandelbrot with a compute shader like this. In this episode, we'll add navigation so you can move around the Mandelbrot set and zoom in. Then we'll implement the ability to change the number of iterations and how we colour them so you can get a more detailed patterns like this. Let's get started. We'll start in our shader display script. We're going to add both mouse and keyboard navigation as well as controlling it via the inspector. The first thing we need to do is remove our hard-coded position in update render texture. Here we set image real and image image to 0. So the first thing we need to do is create some variables for this. Add two serialized private doubles called image real and image image, which will keep the initial value the same at 0. We serialize these so we can test out that it works in the inspector before we add the mouse and keyboard controls. We'll also add the pixel size. I've just hard-coded this to the value of 4 divided by 2160 because my screen is 4K and that's how high the screen is in pixels. You could consider using screen.height. You'll just have to set this value in the start method and I'll leave that for you to add in. You can also add a header to these variables to make it more obvious what they are in the inspector. I've just called it location. In the update render texture function, we can then just change our hard-coded values to these variables. We need to cast our doubles to floats as we're using set float. There is no set double call. I've kept the variables as doubles as we'll want that precision later, but it makes it more complicated. So for now, we'll stick with set float and see how far this takes us. When we change these values in the inspector, we want the compute shader to run to update the Mandelbrot. We do this by adding an onValidate function, which will be called when the inspector values change. Here we simply need to update the needsUpdate variable to true, which will trigger the render in onRenderImage. Back in Unity, we can test this out. You can see changing the coordinates of the center point moves our image around, and updating the pixel size allows us to zoom in. The pixel size is going to get very small, so it's not very easy to use in the inspector. We'll have to manually enter values for now to get the image into the position we want. We don't have a lot of definition now we've zoomed in because we're only doing 32 iterations in the compute shader. We'll add in the ability to change that too once we've finished with the navigation. Let's head back to the code and add in keyboard and mouse movement. The first thing we need to do is add back in the update function that's called each frame so we can capture the input. We're going to use the arrow keys to move around, so let's create a move method. This takes a double for the real and image to indicate which direction we want to move in. We'll be passing in values like 0, -1 and +1 to indicate if we want to move in that direction. The first thing to do is to calculate how much we need to move. Create a double called move speed. This is going to be how many pixels per second we move, which we'll set to screen.height divided by 5. This means it will take 5 seconds to move the whole height of the screen. You can tune this to whatever you like. You could even make it a serialized field so you can modify it in the inspector if you like. Now we have the speed. We calculate the move amount by multiplying this by the pixel size because we're updating the complex number for the center of the screen. Finally, multiplying by time.delta time to get how long has elapsed since the last frame. Now we have that, we can update the center position by increasing image real and image image by our past variable multiplied by the move amount. So if we pass in 0 to real, it won't move in that direction. -1 means we'll get a negative value, so the center will move to the left, and a positive will move the center to the right. We then need to remember to set needsUpdate so that the compute shader will recalculate the Mandelbrot based on the new center position. So back in the update function, we can check if the left arrow is pressed using Input.GetKey and passing in keycode.leftArrow. If it is, then we'll move -1 in the real and 0 in the imaginary directions. For the right arrow, we move +1 in the real. Similarly, for up and down, we'll move up and down in the imaginary direction. Note that I've done this as 4 separate if statements. I haven't used else if. This is because this will allow you to hold down any combination of arrow keys. Obviously, if you hold left and right, you'll not go anywhere, but you can do, say, right and up to go diagonally. The next thing we want to do is use plus and minus to control the zoom. so we need a new zoom method. We take in an int direction. This will say be +1 or -1 depending if we're zooming it in or out. I found that a nice zoom speed is to double the zoom level every second. So to do this, we need to increase the pixel size by direction multiplied by pixel size by time.delta time. You can see that if 1 second has elapsed, you'd be adding direction, which is 1, multiplied by the pixel size. So you'd double it. However, this is problematic if you're zooming in, which is decreasing the pixel size, because then you'd get pixel size minus equals pixel size, which would be 0. So just to handle this edge case, we'll use mathf.min to bound the time.delta time to a maximum of 0.5. You could do this in many ways that are probably more elegant, but this should work. Again, after we've updated pixel size, we'll need to set needs update so the compute shader re-renders the Mandelbrot. Back in the update, we can use keypad plus to zoom in, which is a param of -1, and keypad minus to zoom out, which is a param of 1. Let's jump into Unity and check that out. I can now navigate around with the keyboard and zoom in and out. That all seems to be working well. Let's jump back into the code and add in mouse navigation. Adding zoom to the mouse buttons is easy enough as we already have the zoom method. So to the update method, I'll add 2 extra if statements. I'm using the buttons on the side of my mouse. To get if these are pressed, we use Input.GetMouseButton, passing in the values of 3 and 4. The values 0, 1 and 2 being left, right and middle mouse buttons. I've mapped button 3 to zoom out, so we pass in 1 to the zoom and button 4 to zoom in with -1. To move around with the mouse, we could implement a few different things. One you may think of is to click and drag to pan around. However, one key aspect I like to do is to center on a specific point and zoom in and out from there. With clicking and dragging, it would be very hard to get it centered in the screen to do this. So instead, I'll implement it in such a way that when you click the screen, it focuses on that point you clicked on. We add a new method called centerOnMouse, and we'll code this up in a second. But first, we'll just add the call in the update method. If we click the left mouse button, we'll call this method. You'll note here that I've used getMouseButtonDown rather than getMouseButton. That is because we just want it to fire when you first press the left mouse button, not continuously trying to set the position. Whereas in the zooming, we did want to be able to hold down the button and for it to carry on zooming. To implement the center on mouse functionality is fairly simple. We can get the X and Y position of the mouse using Input.MousePosition, taking the X and Y parameter. This maps 0, 0 to the bottom left. Our point defining where we want to draw the Mandelbrot is based on the center of the screen. So we can simply convert our mouse coordinates by subtracting off half the width from X and half the height from Y. This will give us 0, 0 in the center as we want. Now to update the real and imaginary points that define the center, we can simply multiply the pixel coordinates by our pixel size. Then add this on to our original values. Finally, as with the other updates, we set needs update to true so that the compute shader will update the Mandelbrot visualization. Let's jump back into Unity and make sure this all works. I can happily click around to center on the screen, and this works really well for zooming in to those locations. Now we can zoom in and navigate around. It is really clear that we need more iterations to be able to see more detail of the Mandelbrot. So let's do that now. The first thing to do is to add some more serialized fields to control the number of iterations. We'll use a new header called color setup to separate these from our location variables. The first one will be iterations per group. This will be how many iterations we use in the Mandelbrot function for one pass, i.e. one group, through our color. We're still going to use grayscale for now, so setting this at 256 will mean we show each possible grey shade. If you set it larger than this, you'll just end up some iterations sharing the same color. So we'll bound this using the range attribute between 1 and 256. This is important. Setting it to 0 or a negative number would not work out well for us. We'll also add a second variable whilst we're here called numGroups. If one group takes us from white to black through our grayscale, then we'll make it so you can repeat this again. Again, we'll use a range attribute to limit what we do. There must be at least one group and I've bounded the upper limit to 10, so we never do more than 2,560 iterations in total. I note now that I was too focused on the shader code and I accidentally used snake case naming for the location variables. Oh well, no point changing that now. Now we have these values, we can pass them into our shader. We've not added them to the shader yet, but let's code it up real quick to save us coming back. In our update render texture function, we can use ComputeShader.setInt to pass these variables in. We'll keep it simple and to use the same name, albeit in snake case for iterations per group and num groups. That's it. Now let's open up the Compute shader and make the changes there. First, we just declare our new integers, iterations per group and num groups. Then we just need to update what happens in the Mandelbrot kernel. Currently, the total iterations is hard-coded at 32. We update this to be iterations per group times num groups, as that will be the new total. The Mandelbrot iterations function operates as before, returning how many iterations it took for each point before we ruled it out of the Mandelbrot set. So all we need to do is update the shade calculation. We could simply update the shade calculation to repeat our gradient for each group, but this would lead to sharp transitions between white and black each time. Instead, we'll add an extra bit of logic to invert the gradient for each group. So we'll go white to black, then black to white, then white to black, etc. I'll store our gradient position in a new float called gradient_pos. This will be much like our old shade we've just got rid of. Firstly, we take our iterations for exclusion, then take that modulo the iterations per group. The modulo operator here makes it wrap around back to 0. If our iterations per group was say 4, then this would go 0, 1, 2, 3, then wrap back, 0, 1, 2, 3 again. We can then divide this by iterations per group, which will get us our 0 to 1 value. Again, we cast to a float, so this isn't an integer division. Next, we want to know if we're on an even or odd group, so we can invert the gradient as necessary. We calculate this as iterations for exclusion divided by iterations per group, then take that mod 2. By using division here, we get how many times we've gone through the groups. If again our group was 4, and we excluded at iteration 5, then 5 divided by 4 is 1.25, but because this is an integer arithmetic, it will get truncated to 1. The mod 2 then tells us if it's even or odd. It'll always go 0, 1, 0, 1, 0, 1, etc. Now we know this, we can calculate the new shade. If we're in an odd group, we can just take the gradient pos as our shade value. That's black to white. Else, we'll take 1 minus it, as before, to get white to black. If you haven't seen this syntax before, this is called a ternary operator. It operates just like an if-else statement, but due to shader optimization, it'll normally be faster as no branching will ever be done. The final thing we want to do is to hard code the final value. It could be white or black, depending on how many groups we have. So to avoid it changing all the time, we just hard code the last value to black by checking if the iterations for exclusion is equal to the total iterations. If it is, then we set the value to 0, else we leave shade unchanged. Again, we're using a ternary operator here. That's it. Let's jump back into Unity and check this out. I'll just set the number of iterations quite low and use a few groups so you can see the inverted gradient working. Now it's time to take a look around and see what cool patterns we can find. As you zoom in more, you'll see it takes quite a lot longer to process and your frame rate will decrease. If you're going far enough, panning and clicking will even stop working. This is because we're hitting the precision of the floating point values we're using. That's something else to sort out later. But that's it for this episode. In the next episode, we'll update our code to allow the use of color gradients rather than just grayscale. This should really make things look better. As ever, the full code is on GitHub and linked in the description below. See you next time.